So good morning, everyone. Hope you're well. You have a good night's sleep. You ready for more lectures? Good. So yesterday we talked about two different kinds of topics. One was membrane filtration, and the other one had to do with flocculation, polyelectrolyte flocculation. So I'm going to give you 3 more lectures now. We'll have 2 lectures about flocculation, and then another one about membranes. So I hope that by the end of it, you would have a deeper understanding of what's going on. But please do try to read some of the background material. I think you need to do that to really understand what's going on. It's more than just my slides that will teach you. So for the first lecture, I'm going to talk to you now about another project we've done, which is on polyelectrolyte flocculation. And in this case, we're going to have a project where we look again at the removal of heavy metal ions, but this time we're going to use humic acids. So humic acid, it's a natural form of organic matter which arises particularly in water that comes from mountainous areas. It gives the water a sort of browny color. So it's naturally occurring. And the idea in this project was that we could combine the removal of the humic acid with the removal of the heavy metals, but with the addition, in this case, of a polyelectrolyte to carry out the flocculation. So yesterday we were using surfactants to do the flocculation, and now we're going to use polyelectrolytes. So those of you who are more familiar with wastewater treatment will know that polyelectrolytes are used quite a lot for sludge treatment. Have you come across that? I guess, yeah. Good. So the idea is, in this project, we're going to remove heavy metals. In particular, we looked at zinc and lead. So they may not necessarily be the most important types of metal or heavy metal, but those are the ones that we studied in this piece of work. And we're going to remove them using complexation flocculation. So it's similar to yesterday. First of all, we complex them onto a larger molecule, and then the whole system is flocculated to create larger particles that will either settle or they can be filtered. So we complex the heavy metal ions to the humic substances, the humic acids, by, in this case, electrostatic interactions. And then we add a polymer. So what happens is the humic acid and the heavy metal ions that are bound will be flocculated by polyelectrolyte. So what the polyelectrolyte does is it cancels the charges in the system, and when the charges have been neutralized, everything starts to coagulate and stick together because of hydrophobic forces. And we get a phenomenon known as polymer bridges, which is where the polymers join themselves across a distance to create a kind of bridge. And that gives us flocks which will filter or settle to remove the material. So in this case, we create flocks which contain heavy metals. So in the talk, I'll introduce the topic. I'm going to talk a little bit about complexation and flocculation. I'll then describe the experiments and the conditions that we used. I'll present the results and the conclusions from the work, and of course, who actually did the work. So why are we really interested in this topic? Well, there's 2 reasons. One is that heavy metal ions are a topic of environmental concern. We know that heavy metals have a serious effect on health, both human health, but also of wildlife, fishes, animals in general. So there are lots of regulations and legislation about the permissible amount of heavy metals that can be discharged into the environment. So we do need to control them. So we're seeing increased environmental regulations being placed on the industrial discharge of heavy metals. It's generally industry which are producing them. So we can give a few examples. So here I've mentioned process engineering. Mining's producing a great deal of metal ions, as I mentioned yesterday. but also producing metal products, so any kind of metal working or metal finishing. Also, dyeing industries, textile industries, they produce lots of heavy metals. So it's generally the industry that's discharging them into the environment. I'm going to mention a couple of colloidal-based processors which we previously developed, and I mentioned them yesterday, so it's revision for you, really. Developed to reduce the level of heavy metals. One of them is Micellar enhanced ultrafiltration, and the other one is polyelectrolyte enhanced ultrafiltration. So remember, the idea is that ultrafiltration is a kind of membrane process, but the ultrafiltration won't trap the heavy metals by itself because they're too small. So what we do is trap the heavy metals on larger colloidal molecules that will be trapped. That's the idea. So let me tell you about Micellar enhanced ultrafiltration. So you can see here what's going on. Remember that a micelle is a kind of colloidal particle which is formed from surfactants. And the surfactants at sufficient concentration will arrange themselves in this structure where the hydrophilic head groups are outside and in contact with the water, and the hydrophobic chains point towards the center. So in the center we have something that's a little bit like an oil drop. It's any organic molecule will be very soluble in the micelle, which is why these things are useful for cleaning. But on the outside, because we have these charged groups, then anything that has a charge, in this case the heavy metals, will be adsorbed onto it. So the idea is that we form the micelle, and then we adsorb the heavy metals from the solution. And this structure is quite large, so the distance across here could be 5 or 10 nanometers, and it's large enough to be trapped by ultrafiltration. So we bind the heavy metal to the micellar or the macromolecular surface, or if we have organics, we can solubilize it within the hydrocarbon core. So in other words, this technique can be used both for heavy metals, but also for organic contaminants. So if you have something organic, like benzene, it will go into the micelle. And then the colloid and the target species, so the whole of this is trapped by the ultrafiltration. Now the same idea can be used if we have a polyelectrolyte. So instead of having the micelle, I have this long coiled polyelectrolyte molecule, which is very big, so it will be trapped by the UF. But there are problems with this technique. As I mentioned yesterday, when we use membranes, they tend to foul. So fouling is where we have contamination, dirt, particles which are trapped on the surface, and they reduce the flux of fluid moving through the membrane. So membrane fouling is an issue. We have to stop and we have to clean the membrane, and that's not very convenient. We also find very large retentate streams. That is to say, the recovery of the water phase is quite low. We have a large retentate still trapped behind the membrane. So micellar enhanced ultrafiltration was developed 20 or 30 years ago, but it never really took off because of these problems. And that's why we've tried to develop new ideas. So let's move on then and try to understand a little bit more about complexation and flocculation. How does that work? So here I'm just summarizing again what happens in MEUF. There's my membrane. Here are the micelles. The yellow circles represent the heavy metal ions. So here we adsorb the heavy metal to the micelle or the macromolecule. We move it towards the membrane. And obviously only the free heavy metals can move through, but the ones which are adsorbed, which will be most of them, are trapped. Now in complexation flocculation, something different happens. We take the micelle or the macromolecule, which contains the adsorbed species, but then we add another species, which is a flocculant. So in this case, the flocculant could be a polyelectrolyte. We could also use metal ions, which is what I showed you yesterday, where things are working in reverse. It could be a surfactant, which is what we used yesterday. But you see what's happening. These very small particles are joining together to form much larger ones. And with these large particles, we don't need this membrane. We can just use a very coarse filter. So this could be paper, filter paper, or even we can just settle the particles. And that means that we can separate out the contaminant species from the water. So that's how the complexation flocculation process is working. I hope this slide is clear, that the copy is not very good. If you look here on the right, this is an example of a humic acid molecule. So generally they're sort of chains that are made from aromatic rings, which have side groups on them. And they have a small number of polar groups, but once those polar groups have been neutralized, then in general the chains are very hydrophobic. So it's quite easy to flocculate these. When we treat water that comes from the hills and contains humic acid, we can add something like aluminium or ferric iron, which has an opposite charge, and it causes the coagulation. So classical way to coagulate water which contains humic acid is to add ferric or aluminium, and these will form very large flocks. Now what happens in this case is that we start off with these particles are really the humic acid particles, which I've shown here, and then you see the positive ions are the heavy metal ions. So first of all, we adsorb the heavy metal to the humic acid. So why am I doing this? Well, just to remind you that humic acid is present in certain kinds of wastewaters or raw waters, and we're going to combine that stream with the waste stream that contains the heavy metal ions. And what we'll get is this kind of structure where everything is adsorbed, and we then add the polyelectrolyte. So you see here that the charges in this whole system will neutralize, just like we saw yesterday. The charges neutralize, but now you see that these very large molecules can bridge between the particles. So this is the kind of polymer bridging. We get something like this. So humic acid, heavy metal, and then here is the polyelectrolyte, and it's kind of joining all these dots together. So we get this very large particle, which is really a kind of mesh of 3 different species. And this is much too big to go through a membrane or even through a filter paper. So again, we can create large flocks that can be settled out or just filtered. So here's the key. You can see that's the metal ion. Those are the humic acid. Here's the sort of polymer electrolyte. And this is the membrane. Now, just to remind you, this is typically what happens in a flocculation process. So you start off with some water coming in here. In this case, I've got water which contains metal ions. So I've called it lowland water because it turns out that, at least in England, rivers are often contaminated with metal ions because big industries tend to build their plants on the river for obvious reasons. They can get water, they can discharge water. But there are places, cities in England, which are quite near to mountainous areas. So this work was developed in Nottingham, some of you may know, which is a city in the Midlands of England, but not very far from higher mountains. So we're going to mix this water from the higher regions with the humic acid. Those are mixed together, and then we come to the next stage where we add the polyelectrolyte. So this is polydadmac. I'm not even going to try and spell out the full name of that, but it's a very common polymeric coagulant which is used in the industry. So you should be able to find that. But you mix those two together. Notice that we always have a rapid mixing because, first of all, we just have to bring all of these things together. But typically after that, we have slow mixing, and slow mixing is where the flocculation happens. So really what happens here is we form this mix and we get this charge neutralization. But to get these bigger particles, we need flocculation. And I'm going to put my microphone down so I can explain to you by hand. So when you have flocculation, you have particles that are moving around. And when the fluid is moving very slowly in laminar flow, so we have a very low Reynolds number, laminar flow, the sheets of fluid are moving like this. And And as they move, the particles touch each other, and that's how they start to coagulate. So the way that we flocculate things is by using very slow mixing laminar flow to enable this contact to occur and particles grow. So it can take quite a few minutes. So in a typical coagulation process, we need a time of 20, 25 minutes. That means that it's a very slow mixing, a very large resonance time. So if you see a clarification basin, they're usually very large. Have you ever been to a water treatment plant?
Very close.
There's one near, okay, so you know. That's why they're so big, because the mixing is very slow. You need big times. Okay, so that just explains more or less what the plant looks like. And then, of course, after we've done the mixing, we need a settling tank. So the solids are going to settle out of the fluid, and the waste solids or the other solids will form a sludge. And then the liquid, which is coming off, is going to be ultrafiltered to give you the treated water. Now, in our case, the thing that we're interested in is actually the sludge, because that will contain heavy metal ions. So the idea is that we exploit the complexation and the metal cations onto the anions, the macromolecular ions, which in this case are humic substances. We then bring about a flocculation of the macromolecules using a charged polyelectrolyte, and this leads to a simultaneous removal of both the metal cations and the macromolecules. So in a way, we've solved two problems in once. We've treated two problematic species. We've removed the metal ions. We've removed the humic acid. If we want to recover the metal ions, we can do that as well in the way that I explained yesterday. So the flocculate is removed by simple settling. That's what's easy. Large particles can settle out, and that's much more convenient. Or we could use a filtration using a cloth or a piece of paper, something like that. But the filtrate we get, the water that comes out is clean, and the sludge that's retained on the cloth will contain the materials that we've removed. So let's look at the advantages. Why do we want to do this? It's fairly low energy requirements. We just flocculate the solids and allow them to settle or filter. So in this case, we don't need membranes. Membranes require some pumping, which requires energy. So low energy requirements. We can remove the charged heavy metal ions or the organic contaminants using humic substances. So both of these, well, this thing is naturally occurring. We use the naturally occurring material to remove the problem contaminant. So this is quite sustainable because we're making use of what's already there in nature. We're not exploiting new resources, but we're using what would be considered to be waste resources actually as valuable material. And we recover the solids in a form that allows the concentration of the heavy metals. So if we want to, we can recover them from the flocks by using acids or bases. As I showed yesterday, that will allow us to form concentrated salts. And it turns out that the design for the system is very simple because it's just the same as a standard clarification basin. So if you can retrofit an existing plant with a new technology, that's very convenient. You don't have to build a new plant. You can use the old plant just using a new idea. So let's have a look then at the experiments and the conditions that we used. So what we want to do, here are the objectives, is to try to remove the heavy metal ions from the water streams by this complexation and flocculation process. The first thing we want to do is to determine the binding, the complexation binding, so the strength of this bonding or adsorption of the metal ions to the humic acid molecules. So what we want to do is to determine something like an adsorption isotherm. We can see how well it's working. Oops. And the next thing would be to study the flocculation of this humic acid using a polyelectrolyte, which is in this case polydadmac. And finally, we'll see how effective the process is by measuring the heavy metal removal from the water by this complexation flocculation process. So determine the adsorption, determine the flocculation, and look at the overall removal efficiency. So these are the substances we used. So there's the I gave you a picture before of humic acid. It's a fairly complicated macromolecule, but it does exist in a lot of natural waters. Polydadmac is an industrial flocculant. It's cationic. It's used a lot to treat sludge in the activated sludge process. And then the heavy metals will be zinc sulfate and lead sulfate, which will be removed. The ultrafiltration membranes we use from a company called PCI. Analyzing the humic acid is very straightforward. We can use a UV spectrophotometer and looking at adsorption at 254 nanometers. So you remember that the humic acid has a large benzene ring which adsorbs light almost in the ultraviolet range. So we can just measure the adsorption of light into that ring, and that will tell us, through a calibration, that will tell us what the concentration is. How do we analyze heavy metals? Well, we can use atomic adsorption spectrophotometry. So that's a classical way. So we measure we heat up the ions and we measure the amount of light they adsorb in a flame, and that tells us how much of those atoms are present. Has anyone heard of atomic adsorption? I'm sure it's sort of standard undergraduate chemistry. So here's the apparatus. What we have, it's a filtration cell. This is what we call an exploded diagram, but you can see this is the main vessel where the liquid is contained, and then we seal that with an O-ring, and the membrane's here. So this is the membrane that's being placed against this plate. And then here I have a stirrer which rotates to stir the contents here, and another O-ring to the top. So if I fix this all together, and then what happens is I fill this with liquid, and then I attach this to a gas cylinder. So through here I'll have a cylinder of high pressure nitrogen. So the gas will come in here and it will push down on the liquid and it will force it to filter through the membrane, and then it will come out on this side. So this is really a membrane ultrafiltration test cell, but it's fairly inexpensive. You can buy them fairly cheaply, but it works very well for this kind of experiment. So these were the test experiments we did. You can see humic acids, we used ranges from 10 to 40 milligrams per liter. So these are typical concentrations that you might find in water that's coming from upland mountainous areas. Zinc sulfate and lead sulfate, again, we tested them in the range from 0.6 to 20 milligrams per liter. So this would be a typical value. This would be a very contaminated value, but we've looked at the full range. The polydilyl dimethyl ammonium chloride, which is polydadmac, to give it its full name, again, we're using industry values from 0.1 to 0.5. That's in the ratio to the humic acid. So the ratio of polydadmac to humic acid in terms of weight was from 1/10 to about 1/2. And then finally the pH, we use natural types of pH which range from 3 till 5. Okay, well those were the experiments. Let's see what happened. Okay, first of all, let's explain how we do the measurements. So here's the membrane. On this side is the kind of feed which contains the humic acid. It contains the heavy metal, which of course will either be bound to the humic acid, but some of it will be unbound. And then we also have lead, that's the other ion, which is either bound or unbound. Going through the membrane, the only thing that can move through the membrane is the small molecular weight materials. So the humic acid will be completely trapped. The only thing that will move through are those metal ions which haven't yet been bound. So this is really my clean water, and I would hope that the concentration of these is going to be very small. But if I know what I started at with a feed, and if I then measure the concentration of the species coming through on this side by a material balance, I can work out what's on this side. And therefore, I can calculate the concentration of zinc that's bound to the humic acid, or zinc that's bound to, lead that's bound to the humic acid. So in other words, I do a material balance and I work out how much of the zinc is present in this free phase and how much of it's present in this trapped phase. So the bound ion, we assume that the free heavy metal moves through the membrane, and we assume that the bound ions remain associated with the micelles. So humic acid to heavy metal binding determination, we wanted to really study the effect of pH on this adsorption. This is the adsorption isotherm. How is it affected by the pH? Because we may have different pHs. How is it affected by the ratio of humic acid to metal? Because if we don't have enough humic acid, then the humic acid will be saturated. And if we have too much humic acid, maybe there won't be any more or change. So there's going to be an optimum ratio of these two to give me the best adsorption. Secondly, how well does the humic acid polydadmac system flocculate? So once we put these together, how well do they flocculate to remove the humic acid? So we look at the effect of dosing the polyelectrolyte, the polydadmac, but also the amount of humic acid itself and the effect, again, of pH. Now, pH is a very important factor when we try to flocculate systems, especially systems that flocculate because of charge. Because we know that the pH will have an effect on the charge. It will tend to change the charge on the molecule. So humic acid, it has different charges depending on what pH it is. And if you remember from your chemistry, acids at very low pH, acids are actually neutralized. So they're an acid group with a proton bound together, and they have no charge. But if you go to very high pH, then the proton is removed, and you have free acid. And that means it will have a greater charge. So it makes sense that a humic acid would probably adsorb more metal ion if we run at higher pH, but we can have a look at that. So the effect of pH and also the amount of heavy metal itself. So let's have a look at results. So first of all, in the graph on the left, I'm plotting the removal efficiency of, and I can't even read that now, I think it's one of these two species. So I've got zinc, which is the square symbols, and lead, which is the circular ones. But you can see that as I increase the pH from 3 up to about 7, you can see how the adsorption is increasing. It increases and then it levels off. So here, look at lead. It's going up to there, and then at pH 7, it's leveling off. So what's happening here is the humic acid, as the pH changes, as the pH increases, the humic acid becomes more and more charged. It's dissociating. So the HA, the A separates from the H. That gives me a negative humic acid anion, which will then adsorb for the lead. So you can see that the best adsorption is really around neutral. So we really would like to have systems operating at about neutral pH. On the right, you can see what happens as I increase the ratio of humic acid to metal. So I have a fixed amount of metal. I'm going to increase the amount of humic acid. And you can see that there's very little change, actually. So as I increase the amount of humic acid, the actual removal efficiency of the two ions remains about the same. So what's happening is, first of all, binding's increasing with pH, but you can see there's very little change in the binding above a ratio of humic acid to metal to 1. So that's the ratio of 1 is probably about there, which is where it's leveled off. And then going up to here, there's no change. So there's no need to have a large amount of humic acid because essentially it's not being used. So we have an excess. So if we arrange for the humic acid metal ratio to be about 1, so we mix our streams in that way, then we get a very effective use of the humic acid to remove it. Also notice that in this case, the zinc is removing less effectively than the lead. See the lead is removed up to about 95%, whereas the zinc is only removed to 65%. So even though both of these ions have 2 positive charges, they're divalent, but there's a difference here. And that's because the interaction of metal ions with polymers, it's specific. So there's more going on than just the electrostatic interaction. There must be some kind of specific interaction between the two species, which requires more chemistry to understand. So you know that intermolecular forces, there's lots of different contributions. We have electrostatic forces, we have van der Waals forces, we have hydrophobic forces. There's a lot of chemistry going on here. The next thing then is to study the effectiveness of the flocculation. So what I wanted to do now is to look at the effect of dosing of the polydadmax. So you would expect that by adding more and more of the flocculant, I'm going to be able to remove more and more of the material. And so what I did was I fixed my pH at 7. I already decided that that was a good pH to work at. And I tried to measure the removal efficiency as a function of the ratio of the polydadmax to the humic acid. So this is the ratio of flocculant to the removal agent. And see what happens. If I have a very small amount of polydadmax, there's virtually no removal. And then suddenly, when I get to a ratio of about 0.3, it jumps up. And at 0.35, it's already shot up to 85%, and then it levels off at about 90%. That's up to about 0.4. Now look what happens now. If I continue increasing polydadmax, it's dropping again, which is weird, right? Well, what's happening is the polydadmax is a flocculant. But if I use too much flocculant, I redisperse my colloid. So in fact, you not only do you neutralize the charge, but you oppose it. So this is a very important lesson to learn if you're designing flocculation systems. If you use too much flocculant, you'll actually go back to where you started. You will redisperse the material. So some people are nodding. They must have seen something like that before, right? So that does happen. You have to be very careful about dosing. So obviously, there's, as we saw yesterday, there's a sweet spot, there's a honey spot where you get the best removal, but it's very, very sensitive. This window is quite narrow. Now let's have a look at the same thing, but now we're going to change the pH slightly. So in this diagram, I'm doing the same thing as I'm doing here, but between the different curves, you see I'm changing the pH. So the black points are pH 3, the red points are pH 5, the green points are pH 7, and the blue points are pH 9. So what you see basically, if you look carefully, you can see there's a kind of maximum point, which gives me a maximum dosage. But as I increase the pH, it's moving up. So whereas at pH 5, let's say the optimum dosage is probably 0.25, if I move to pH 9, the optimum dosage is about 0.4. So what's happening is the polydadmax itself is getting more and more charge. And the higher the charge is, the higher the ratio needs to be of polydadmax to remove it. So that makes sense, doesn't it? You have a bigger charge on your material that you're trying to remove. You need a bigger charge in your flocculant to neutralize it. So all of this is shifting up. But it kind of indicates really that if you go to high pH, you're going to end up using more flocculant. And it may be difficult to go to high pH without adding more chemicals. So really we'd like to work at neutral pH if we can do. So the flocculation is passing through a maximum as a function of the ratio, but also the optimum dosage is increasing with the pH. So now let's have a look at what happens as we change the humic acid concentration. So what I've done is, again, I've looked at the removal efficiency of the humic acid as a function of the ratio of polydadmax to humic acid. But in this case, instead of changing the pH, I'm going to change the amount of humic acid itself. So point A, which is the black line, is using 10 milligrams per liter. Point B, or line B, which is the red line, is using 20, and then line C, which is 40, is the green line. So what you see is that for the black line, you can see there's a very narrow peak there. But as I go to the red line, you see it's broadening out. And then for the green line, it's really very broad indeed. So you have a very, very big maximum. So what that's telling me is that the flocculation is occurring over a broader region at higher dosage. Now remember, this flocculation occurs by polymeric bridging, but certainly for higher humic acid concentrations, this curve is wider, and that means it's less sensitive to the choice of ratio. So in other words, the system is more robust. And it's always good to have a process that's robust because it works well under different conditions. A process that's very sensitive is very easy to break, and we want it to be robust. So it kind of suggests that we should run at these higher concentrations. Now, let's have a look at the effect of polydadamac dosage. So again, we have on this axis the ratio of polydadamac to humic acid, and here I'm going to plot the removal of both the lead ions and the humic acid. So you can see that, as I showed you before, at neutral pH you get this sweet spot. So this is where the humic acid is being removed most effectively. So we're getting the best flocculation just about here, as we saw before. But what we didn't do is to study how well the lead is being removed as a function of this ratio. So how does the removal of lead correlate with the flocculation? And what we see is that it's moving through a maximum again at the same point. So this, you see here, that's moving to a maximum, and the lead is also moving to a maximum at the same point. So there's a correlation between the flocculation and the lead removal, and that makes sense because really we'd expect that to be the case. We'd expect a maximum removal of lead to correlate with a maximum flocculation of the humic acid. So that kind of makes sense for us. If we look here, we can see how this removal efficiency of the lead is correlated to pH, and again you see how it's passing through a maximum, and that maximum is changing because we know that the flocculation efficiency is also changing with pH. So generally the metal removal will increase with pH because we know that the best flocculation is also increasing with pH. So you see pH 3, in the earlier graph I showed you, it was quite poor, starting to increase to pH 6, and there's pH 7. At pH 9, I have almost 100% removal. So if I go back to this earlier graph here, where I had quite a poor removal of zinc, maybe the way to solve that problem would be to use a higher pH, so I have a better adsorption. But notice there is a difference between the two. Okay, so we can see that maximum removal occurs for maximum flocculation, which is what we expect. But we can also see how that then leads to the result that better metal removal occurs with increasing pH, which is those maximum. Let's do some more work now where we look at the effect of the actual humic acid concentration on the removal of the ions. So again, here A, B, and C, I'm using 3 different concentrations, 10, 20, and 40. But in all cases, you can see that there isn't actually a very big difference in the removal, and they're all moving through this maximum at the optimum dosage. So where I have an optimum flocculation, you can see I'll have a maximum removal, which in this case is between 70 and 80%. And obviously this can be optimized by changing the pH. How does the metal concentration affect its own removal? That's a good question. So in other words, if I increase the concentration of metal in the feed, how well can I remove that at the higher concentration? And again, A, B, and C, I'm plotting squares, circles, and triangles. They're all pretty much the same. They're all about 95%. So that means that even if I have relatively high concentration of metal ion, they'll all be removed quite well. So that's good news. So the process is robust to the concentrations. So more metal ions are being removed at higher humic acid concentrations, and the metal concentration has little effect on the metal removal. So that's what they show. So it looks as if it works quite well. Let's have a look here at the effect of lead concentration on the humic acid removal. So does that affect the flocculation? So what we find is that as we go from A, which is black, to B, which is the red, and then C, which is the green. So you notice how the removal efficiency of the heavy metals is, the optimum is changing slightly and the value is dropping. So the effect of increasing the metal concentration is similar to that of decreasing the pH, in the sense that the optimum ratio of flocculant to humic acid is decreasing slightly, just like we saw with decreasing pH. And we see that the adsorption itself is dropping slightly. And that, so the effect of increasing metal concentration is similar to decreasing pH. And that makes sense, because if we decrease the pH, we're going to decrease the charge on the humic acid in the same way that if we increase the metal concentration, which, remember, that's adsorbing onto the humic acid, it will have the same effect. It will decrease the charge on the humic acid. So going from black through red to green, you can see that the optimum flocculant dosage is decreasing. We need less flocculant because we have more heavy metals. So really, the heavy metal ions acting as a self-flocculant. It's helping to neutralize the charge on the humic acid, and that means I need less additional flocculant to remove it. So that's like we saw yesterday, where we added surfactants, we added heavy metal, but the metal itself was helping to reduce the need for more flocculant. So it all adds up to a kind of self-sustaining process. That's the point I'm making. So what are the conclusions that we can make from the study? So what we know then is that as we increase the pH, the charge on the humic acid will increase, and therefore the binding of the metal ions to the molecule, to the humic acid, will increase with pH. So this is good news. It means that with neutral pHs, we can remove most of our humic acid. Secondly, we found that the flocculation of the humic acid is passing through a maximum, and that maximum very much depends on the ratio of the polymer, the polydadmac, to the humic acid. What we also found was that that ratio was increasing with pH. That's because as we increase the pH, the charge on the humic acid increases, and therefore we need a corresponding increase in the amount of oppositely charged flocculant to bring about the flocculation. Thirdly, we found actually that adding more humic acid tends to broaden the flocculation region. It makes it less sensitive to the conditions, and it also increases the amount of lead and zinc that we remove because we have more adsorption sites. So really, having a slightly higher humic acid is advantageous because it increases the removal of the ions, but it also allows us to have a less sensitive and more robust process. Finally, we found that the binding of lead and zinc increases during the flocculation. So as well as binding the lead and zinc to the humic acid in the first phase of the process, when we then do the slow stirring to carry out the flocculation, we actually found that the binding was increasing. So let's just go back to see that more clearly. Yeah, maybe it was here. So this is after the actual flocculation, but I was just trying to show that you can get these numbers up to 100%. And that's even higher than we had at the beginning. So I've gone from 95 to about 100%. So if we play with the process, we can get almost perfect removal. So that's good. We also saw that increases in the amount of lead or zinc led to decreases in the flocculant dosage. So this is an advantage because it means that we have a self-flocculation. The more of these ions, the less of the polymer we need to add. So that's a kind of advantage. Finally, I would say that the complexation flocculation process should be of interest for the removal of heavy metal ions during water treatment. So I think the focus here was really just to get rid of the heavy metal ions. But if those heavy metal ions were of value, things like copper or platinum group metals, things like that. You might want to have an additional process that can recover the metal ions. But in this case, I was thinking about the metal ions during the water treatment to make clean water that can then be returned to the environment. Finally, I'd just like to acknowledge my MSc student, so that's Lunar from China, who did this work a few years ago. Okay, and that's the end of the talk. So, it's about 1 hour, wasn't it? Let's start with some questions or comments. So, Jonathan.
Hello.
Hi.
My question is, if my wastewater treatment plant is in a place there where there's no humic acid available or enough humic acid, can I use a synthetic humic acid or something?
Absolutely. So the idea behind this project was very geographical, that we happened to be in a place where there was a large river basin, the River Trent, which is a large river basin in England, which is only about 50 kilometers from a mountain range called the Pennines, which is the largest mountain range in England. So we could co-locate both of those activities because both of those water streams were available. So the humic acid stream is actually a potable water stream. We're just trying to remove it. But the metal ions are coming from industry on the river. But actually, to answer your question, the process probably works better with a synthetic one, because as you know, real humic acid is a mixture of different things, not only humic acid, but fulvic acid. There's a wide range of molecular weights, and that makes it more difficult to control. So always, if we use synthetic, man-made, idealized streams, we can do better because we can control it better. So I would say we can do both, but it's a good point.
And what's the other question?
You can make a comment if you want. You can say that my talk was awful.
No. And this is more adequate for wastewater treatment because I'm using polymer, and is it adequate to use for water, for drinking water?
Yeah. So in this case, I think the objective of the treatment would be to create a clean stream that can be discharged back into the environment, but I wouldn't advise it would be used for potable purposes. Yeah, I mean, polyelectrolytes are used for potable water clarification in some cases. So not polydadmac, but there are polymeric aluminium compounds which have been used quite a lot in the USA, for instance, for potable water clarification. The reason being that the traditional coagulants, things like aluminium and ferric, and aluminium in particular was associated with Alzheimer's disease, so they stopped using it in America because it could be a little bit toxic. Whereas in England, I think we mainly use ferric coagulants, and I think in Brazil it's mainly ferric too for the potable water. But you could use polymeric compounds for that. But certainly, I think the intention here is to create a stream that could be discharged back into the environment so that it wouldn't be toxic to fish or something like that. So it's not always necessary to create, I mean, we were saying yesterday, what do we mean by clean water? I mean, clean water for human drinking purposes is incredibly pure. There's virtually nothing in it apart from a very small amount of minerals. But do we need to produce such large amounts of clean water? We don't need to drink it all. I mean, we said yesterday you consume 200 liters a day. Where does it go? It goes straight down the sink or down the bath or the shower, cleaning your car. It doesn't have to be so clean. But if it's going to be discharged back into the environment, it needs a certain level of cleaning treatment to work. So it suggests that really you need to have two water streams in water supply. One is for drinking purposes, and one is for other purposes, what we call non-potable purposes. And I think that may be actually the future. That may be the way we have to go to conserve our water, because we just waste too much water. You know, we have all this water, we don't drink it, we don't need it. If you lived in a desert or a very dry area and you didn't have a tap, you'd quickly know the value of water, but we don't know because we're spoilt, right? Any other points? Gentleman on the left. Give your name,
Sorry.
please. Say who you are and where you're from and all that.
Okay, so my name is Bruno. I'm a master student here. And I'd like to know what's your idea of how does that work, that separate treatments, one for like normal uses and another one for drinking water. How would we separate that?
Well, a water treatment plant has 3 or 4 stages. There's a primary treatment, a secondary treatment, and a tertiary treatment. But as you move down the line, the process becomes more and more expensive. So a primary treatment is mainly to remove large particles or you know, leaves or branches. And a secondary treatment would be to do some coagulation and flocculation. And I believe that both of those are probably necessary for any kind of future water use, because the things that are in there have to be removed. But it's the tertiary treatment that's very expensive, because this is where we disinfect, we add chlorine, this is where we do oxidation or ultraviolet treatment, all of those advanced processes or membrane treatments which are very expensive, and it's not necessary. So it's enough to remove large particles and remove colloidal materials to get a clear water. That can be used for irrigation, for instance. You know, irrigation water doesn't have to be disinfected. But if it's going to be used for human drinking, then you need to have those additional. So I think what you could have is a single plant, but after the secondary treatment, you then have 2 branches, and one would be the potable stream, which would be very small, but it would be very high quality and could be even better than we have. And the other stream would be non-potable, which would be destined for cleaning, for washing, for farming, etc. So that may be one way that we could achieve that. But obviously we don't do that, and it's a good question why. Maybe it's too, is it difficult to design, or is it to do with nobody knows?
I think everyone is like settled. They don't need to change. They don't want to change.
Yeah.
But you said yesterday about, you told us about Australia, that they are using that.
Yes.
Do you know anything about acceptance of people, of the society?
Yeah, it's very accepted. I mean, if you've lived in a drought for 10 years and you've had your water supply continuously cut off, you'd rather be in a situation where something is coming out of the tap. If it's in 2 separate streams, who cares? If you have access to drinking water and you have cleaning water, then that works very well. So I think if you have to live in a situation where you're in a drought, you learn very quickly to deal with the hardships. And it has been very well accepted in places like Sydney and Melbourne, where it's very dry.
Thank you.
And I would like to know a little bit about what is the cost of this, of using these polymers comparing with the traditional coagulants?
They're about the same. They're not expensive. I'm not sure if I can give you an exact cost off my head. So they obviously buy these materials in very large quantities, in bulk quantities, because if you buy in large quantities, it's less expensive. So if you buy, you know, a ton, which is 1,000 kilograms, I guess you might pay $10 or $20. You know, you're going to use a large amount of these materials. And you've been to water treatment plants, I have. They're delivered in very large tubs or barrels, and they use a lot of this material, you know. But the cost of a polymeric flocculant isn't very different from an inorganic one like aluminium or ferric. So they're not intended to be expensive. And indeed, the humic acid comes for free, so you don't have to pay for that. So I think the costs are manageable. And as I was explaining, the energy costs should be quite small. But certainly they wouldn't be any more expensive than a normal clarification plant. So the cost of the water that's coming out from that wouldn't be any different either. And that's the advantage here, of course, is that we can we call it retrofitting. It's where we redesign a plant to do a new job with the same equipment, retrofitting. And the retrofitting here wouldn't cost very much. So it's intended to be economical.
And also thinking about life cycle assessment, do you know how we do these polymers? Like if it has a deep impact in the nature or something like this, the energy costs also?
Well, I believe that life cycle assessment of polymeric coagulants has been studied quite a lot in the water industry. So they look at the impacts of the manufacture and the distribution and the usage and even the disposal. I don't know the details of that, but I understand that it's manageable. It's not thought to be a very serious impact. And indeed, I think the polyelectrolytes over time can be biodegradable, so they don't persist in the environment forever. Certainly heavy metals are more serious, and that's what we want to remove. But it's a good point that if you use any kind of process and you want it to be sustainable, you have to look at the life cycle and assessment. And that means that you look at the whole process from the manufacture of the materials and the supply and distribution, the use, and then the disposal. So it's a very long chain. And really you have to look at that if you're thinking about the sustainability of the whole process.
Okay, thank you.
Sorry, just one more. As she talked about the production and everything, we have some difficulties to talk to the private sectors here in Brazil, the university and the private sectors. How is that relation in the United Kingdom? Do you have, like, for example, a company interested in that research so that they can produce that polymers?
Yes. So the water industry in the UK was privatized about 25 years ago under the government of Margaret Thatcher. You may remember her. So what happened until that point was the water companies were all state-owned and state-operated, but they were privatized, so they were floated on the stock market and owned by private owners, but they are still regulated by the government. So for instance, where I work in Oxford, our water authority is called Thames Water. Thames is the main river basin of London and the southeast of England, and they have the control of all of the supply of potable water, the treatment of wastewater, and all of these things. And yes, I've done quite a lot of work with them. I've had a couple of large projects, which I'm not going to talk about today, but I've done some, for instance, I did some work for them on a large reservoir they have near Oxford, where they had a problem of algal blooms. So you're familiar with algae which grow on the surface of the water. They have to be removed before the treatment process. It's quite a big problem, actually. So we work with them on that, and they are receptive to research projects. However, and this is a big however, you know as well as I know that water companies are very, very conservative. They don't want to play around with their process. If it works, it works, right? If it ain't broken, why fix it? That's what we say in English. So if something works well, don't play with it, especially if it's so important, because this water supply is crucial to the survival of people. And if something goes wrong, even if the water supply is disrupted for half an hour, it's a huge problem. And they're going to get complaints, and they're going to have lawsuits and things like that. So the reality is that they're very, very conservative. It's difficult for them to even think about changing their practice. I had a project with another water company some years ago. So I moved my job. I used to work in Nottingham. Now I work in Oxford. So in Nottingham, the water authority is called Severn Trent. So there's the Severn and the Trent, and that's the biggest river basin in the southwest of England. And we were looking at retrofitting a treatment plant using membranes. And we even installed a membrane on their plant, and it worked. Everything was working fine. But they didn't want to change, you know, and I thought, why not? And it's because, oh, it works well, so we don't want to change it. So even if they know that you have a better technology that works better and it's going to improve things, they may not change it because for them it's a risk. So this is the problem that you're going to find. If you deal with, you're in the university, if you deal with water authorities or water companies, they're very, very conservative. And if you want to change anything at all, it's going to take a long time. So you have to be very patient. But of course, if you do make a change, it's going to have a very big impact. So my advice is be very patient.
Thank you.
Okay.
Hi, Professor.
Hi.
Thank you for your lecture. My name is Mariana. I'm a PhD student here in the program. I'd like to know if you have any research about this cost reduction that is possible by optimizing the coagulation flocculation process, because this impact on costs, isn't it?
Yeah, yeah. So when you design a coagulation flocculation process, it does have to be optimized across the process. So the first thing that you would look at would be the dosage of the polymer or the coagulant. The second thing you would look at would be the mixing, so the rapid mixing or the slow mixing. There's quite a lot of different things to look at in the process. In the lab, we use a thing called a jar tester. Have you come across that? So it's a device which allows you to control the speed of mixing and the volume of mixing, and that allows you to do an optimization. The point is that it's very difficult in practice because the quality of the feed water is changing, and it changes very rapidly if you have a storm event. So if you have a very big thunderstorm like we had a couple of nights ago, or you have a flood, the water changes very quickly. It becomes turbid, it contains much higher solids, higher organics. And what you'd really like to do is to have an online control so that you feed the information into the control plant. And as of yet, we don't have that. So I had a project where we were trying to do such a thing by measuring the composition of the feed water in terms of its colloidal charge. And you could actually invent a device, but we ran into the same problem. Too complicated for the water companies. They have laboratory technicians in white coats who take a sample and then tell the plant operator. It takes hours to go from one to the other. So the fact is that we can't respond very quickly to what we call storm events, which would actually save a lot of money and be effective. So I think in the long term, it's quite easy to optimize a plant. You have time to check all these issues of the dosing and the mixing and so on. But what we can't do is to respond very quickly. And if someone can invent a device that the water companies would accept, that would actually have a very big impact. So I think it's an area for future research.
I have a question. I was wondering if we can use flotation instead of setting,
Yeah.
and increase the flux rate and make it more compact, and the flocculation time could be shorter.
Yeah, you speak like a man of experience, actually. As you know, there is such a process. It's called dissolved air flotation. So what we do is we, instead of settling the particles, we introduce a stream of very tiny air bubbles, which obviously float up. And the air bubbles have the property that they will stick to the hydrophobic particles, and therefore the hydrophobic particles float up, and they can simply be, scraped off. And they've actually tried that. And as you said, the advantage is that you can reduce the footprint of the plant. So when you build a water treatment plant, one of the things you have to worry about is the area, the land that's being required to build that plant, because it's more expensive if it's bigger. So we try to make it more compact and reduce its footprint. And that gives us a more effective throughput. So we can measure it in terms of a thing called LMH. Have you come across that? So it's liters per square meter per hour. And the higher the LMH, the more effective the water treatment plant is. And if you go from a simple clarification basin to dissolved air flotation plant, you can increase it by a factor of about 5. So it's very effective. But it's also expensive because you have to pump the air. And, so it has been used for quite a lot of applications. Yeah. Good point.
I have another question also. You talk about the different types of water that we can have for drink or to another uses. And that actually, it's really interesting for me because I'm working with water reuse through runoff, stormwater. And a difficulty that we have here in Brazil is that we don't have specific legislation for water reuse. So we cannot use it because it's not regulated. And also, a question that we have a lot is how we can assure that we don't have risks to the population or to the environmental with the quality of the water that we have there. So I would like to know, in the UK, you have some legislation about water reuse, or also, and also how we can measure, how we can assure that if we treat the water less than to potable uses, it will be good for use for just contact with humans. I don't know if it was clear, but...
Yeah, I think I get the point. And the answer is no, we don't have regulations on large-scale water reuse. There are some regulations coming into effect about how we do that process, but to reuse water on a large scale is something that doesn't happen in England. All of our wastewater goes straight back into the river basin, and it's going into the potable water treatment plant, so it's being treated again. So in a way, there's no need to think about that. A lot of people have fears about reusing water. Is it going to be safe? But some people have ethical difficulties with it. So for instance, in the Islamic world, the Muslims believe that a water that's passed through a human being is not pure. And the way they've solved that is that the water is then re-injected into the ground. So it's called indirect potable reuse. If it goes through the ground, it becomes filtered and treated, and it can be used again. So in the UK, we don't have regulations about water reuse yet, because we don't do that on a large enough scale. We just dispose of the water. But I imagine that would eventually come into effect. And as to what kind of regulations we need for potable water or non-potable water, I think you have to be a little bit careful, because even non-potable water, if it comes into contact with human beings, even without drinking, could cause infection, because it can spread certain kinds of diseases. So it's a tricky question. I'm not a microbiologist, so I don't know exactly, what the issues are, but you'd need a legislation which involved scientists to try and work out what the issues are, but also the lawyers and the politicians to decide what's appropriate. There probably isn't a big pressure on water reuse yet in Brazil, but it may happen in the future. So it's one of those things where the needs must, that once the necessity arises, I think those things will come into effect. And they already have in Australia. So have a look at Singapore, have a look at Australia, because in those countries there's a very high level of water reuse. So I mentioned yesterday new water, so it's spelt NU water, but that water is recycled from municipal domestic wastewater treatment plants, and it's being used for drinking. And you wouldn't know. I mean, it's absolutely pure water. You may not like the idea of that, but don't worry about it, because it's perfectly clean. So I'm not the expert on that. We don't do that in the UK, but I recommend that you try to find out things that happen. Certainly in Singapore, there's a lot of information there. Look up new water, NU water, and have a look at the water drought in Australia and what they've been doing over there. I don't believe there's a lot of water reuse either in the Arabian Gulf region, even though most of their water is desalinated. So they'd rather desalinate more seawater than recycle what they have. But I think efforts are starting to come into effect even there. So there's a lot out there that you can find.
Hey, I'm Camila. Thank you for your lecture. I would like you to comment a little bit about how could we apply these technologies that you've mentioned in the factories themselves? Because we keep talking about how hard it is to play around with technologies
Yeah.
in wastewater treatment plants, in water treatment plants, but what if the industries themselves treated and removed these contaminants we've mentioned before sending them to the stations?
Yeah,
Please.
I think that's a very good point. Let's ask ourselves a question of why they don't do that. It's because they don't have to, because obviously it's more expensive for them. And what you need is legislation. It's the only way that you can force industry or anyone else to adopt new practices, which is not going to add to their profit margin, right? It's not going to add to their profit line. So you have to force them to do it by legislation. But in a way, it helps them, because if people, if they can recycle it, it may help them. But if people see that they're more environmentally aware, they may get more people buying shares. You know, if you want to invest in a company, you may invest in a company because you believe the company's green, that it's sustainable. So it may attract more investment. So there are large companies who already do this kind of recycling on their sites. So a good example, I think, is Coca-Cola. They've been doing it for many years, recycling of their waters. But there's other companies that are getting involved in this. But here's a point, that if you design a process, maybe you should design a process that doesn't create this waste in the first place. So what we're talking about now is end of pipe. Yeah, end of pipe. The pipe that comes out of the factory and the waste that comes out, we want to treat that. Well, maybe we shouldn't even have that waste pipe, because if you design the chemical process to make those materials, if you design it in a better way, then those materials can be recycled inside the process. And that's not even end of pipe, that's in process, you know. So I think there's a lot of potential for development in the industry itself, that if the companies, if the industry can do their manufacturing in a more sustainable way, where they themselves worry about internal recycling and reducing this waste problem, it's going to be much better. Think about it, if you have a more efficient process, you don't create waste. How much energy does that require as compared to having an end-of-pipe waste that then has to be treated? You don't even have to think about it. You know that the second alternative is a lot more expensive. So we have to join these things up. You know, we have, here's the company making the thing, here's the water company trying to treat the wastewater, here's the public receiving the wastewater. They're all the same people, just wearing different shirts, right? So we have to join people together. That's the only way that sustainability can work, is if we all pull in the same direction. So I think it's an excellent point you make. The companies have to do more, but they won't unless you hit them.
So good morning. Thank you for your lecture. My name is Maria Cecilia. I'm a master's student here. And I don't have a question exactly. I just want to make a comment that you said maybe people wouldn't like the idea of drinking reused water.
Mm-hmm.
But we had a class last week, and a professor of ours commented with us that we are already kind of reusing the water, because we're getting water from downstream places we're disposing them, the sewage. So
Yeah.
it's just a matter of how the information is communicated.
Exactly, yeah. So what do we mean by all water is recycled? The water that falls out of the sky is recycled from the sea, and the water in the sea is recycled from the rivers and from the waste process. So water's going round and round and round and round. I remember when I was at school, we were asked to do a calculation. Here was the calculation. How many water molecules in my body that once were in the body of Leonardo da Vinci? You can do the calculation. It turns out to be about 100. There's 100 water molecules in your body that once went through the body of Leonardo da Vinci. So all the water's recycled. It's only a question of attitude, as you say.
I think we can go to the coffee break and then go back like in half an hour.
Yeah.
So now it's 9:35. We can go back 10. Okay?